Thank you for your interest in my presentation. This is Wayne Strasser. I'm going to be speaking very quickly, and I recommend playing this back at partial speed if you actually want to understand what I'm saying. Our motivation is that we have two simultaneous problems that we can solve with one solution, whereas we have waste management challenges as well as continuously increasing energy demands, as illustrated in the cycle on the right-hand side of the page, where we eat, excrete, and heat, and that can produce a self-sustaining cycle. We're focused on direct spray injection of highly concentrated biosludge in any type of energy harvesting equipment. The challenge is that because of varying composition of sludges, whether it be human waste or animal waste, widely varying viscosity as composition changes in time, we introduced this concept of smart atomization. Uh, this is not our first presentation on this topic, but we use two independent PNID controllers working in tandem actually to mitigate the effects of varying viscosity. And our work here is to implement that for smart atomization of biosludge. Our atomizer design is shown on the right, where steam is in a central region and biosludge is in an annular region outside that. The steam not only assists by producing shear, but it also reduces the viscosity by heating. The downside is that steam reduces boiler efficiency if you're going to be using this in incineration, so we want to minimize the steam usage. We have two flow controllers. The first is called C1. It automates the flow of biosludge based on pressure drop because as equipment limitations prevent you from too widely varying viscosity, we have a way to mitigate that. The second controller is what we're calling C2, and that automates the flow of steam based on droplet size. We'd expect as the viscosity increases, we would need more steam to keep the same droplet size. Our earlier test in source one, which we'll have on the last slide as our sources, was a small region, a 1/32 of an azimuth with periodic boundary conditions, an unconventionally coarse mesh, and the purpose was as a proof of concept of this coupled controller system. Now, however, we're going to do a better job. We're going to have a 45-degree azimuth with porous media to simulate pressure drop and an overall piping system. We don't want to have a large piping system in CFD, so we have a compact way of doing that by having porous media where we expect pressure drop to be linear with viscosity, and we have a more refined mesh. We implement these two independent controllers using user-defined functions in Fluent. On the right-hand side is a brief overview of our method, and we can discuss more if you're interested. The animation on the left-hand side of the screen is for our atomization system. It's an isometric view where the injector is on the left, the pulsing biosludge is on the right. The blue represents the interface between the sludge and the steam. We see this bulk instability, bulk unsteadiness, creating this pulsing flow and amplifies those instabilities to help atomization. The time scale of that bulk bursting event up close to the nozzle is about 0.001 seconds. Here's a side view of that same scenario where, again, it's just an instantaneous snapshot. But the biosludge is in the annulus, steam's in the center, as previously discussed, and we see this radial bursting event here that's caused by waves crashing radially and spreading the sludge out and helping it to atomize. An interesting result of that pulsing you saw on the previous slide is this spatiotemporally fluctuating droplet size, where the plot below is solder mean diameter on the ordinate, and abscissa is normalized distance from the orifice. And we see these waves of higher solder mean diameter moving through the domain from left to right, and we've animated that in the following video you see on your screen. And because of those radial bursts, we see this bulk general motion of higher droplet waves making their way through the domain. The information you've seen on the previous slides can be condensed into a single Hovmöller diagram to indicate space-time correlation in the droplet size. So what we have here on the abscissa is normalized distance from the orifice, and on the ordinate is normalized flow time, where the actual time has been normalized by a convective time for a mixture to move throughout the atomizer domain. And on the color axis is solder mean diameter, and what you see is these three nice repeating units as waves are moving from left to right through the atomizer, and these are occurring at a unit time of about 20 convective times. Our goal now is to demonstrate that we have controllers that can mitigate the effects both in pressure drop and droplet size management problems by a 100-fold increase in viscosity. So we take our Newtonian viscosity from 0.05 to 5. Before the viscosity increase, there were no controllers engaged, and we're going to look at three scenarios. The first is C0, where no controllers are involved, C2, where only the C2 controller is involved, and then C1 plus C2 where they're acting independently, but we're coupling them together to allow them to work in tandem. Now recall that C1 is the biosludge flow controller and C2 is the steam flow controller. Let's begin by investigating the response of Biosludge flow controller C1 in all three of those previously described scenarios. The figure in the bottom left-hand corner is normalized pressure versus time, where one on the normalized pressure axis is where we begun, which is our set point, and the normalized flow time again is the absolute time divided by the convective time scale. On the bottom right-hand corner is the normalized biosludge mass flow rate, where 1 is where we began. And we see that in cases C0 and C2, in both of those where the biosludge flow was purposely held constant, we see pressure increase by around 450%. That's pressure drop, that is. And then the C1-2, where everything's being controlled, we see biosludge flow decreasing, and the pressure returns to set point, which is our goal of that controller. So the conclusion is that C1 is necessary to maintain biosludge pumping requirements where that pump is limited by pressure drop. Now we begin to look at the steam flow controller response, which is C2 during all three scenarios. The two figures at the bottom are similar to the previous figures, except that now we're looking at normalized solder mean diameter in the bottom left-hand corner, where unit T would be where we begun, or the set point. On the right-hand side is normalized steam flow, where 1 is where we begun, and that would be the set point. So for C0, where we held all flows constant during a 100-fold viscosity increase, we see the solder mean diameter increase by 180%. We expected the diameter to increase with increase of viscosity, everything else held constant. However, for C2 and C1-2, where steam flow was adjusted, in both of those cases, we see the solder mean diameter returning to set point. Now, the normalized solder mean diameter is a noisy response, but we're speaking of the time average. So the conclusion is that C2 is necessary to maintain atomization quality. I want to point out a couple of things on the right-hand side. For C2, where we have a constant biosludge flow, the green on the bottom right-hand side, the flow is continuing, the steam requirements continuing to increase with time, and we didn't have the time to let that steady out. And interesting occurring with C1-2, where we're adjusting the steam and the sludge flow, the steam flow requirements actually falling off. So lessons learned from a biosludge flow standpoint. First, the biosludge differential pressure across the porous media or across the inlet increased by only about half of the viscosity change. We were shooting for 100, we only got it in the low 50s. And why is that? Well, we realized after doing so that our starting pressure drop was not just the porous media. We're talking about the whole inlet. So it was porous media that was about half the pressure drop affected by the viscosity. And the rest of it was the differential pressure created by the biosludge breaking through the steam interface. So we didn't get exactly the pressure drop increase we were looking for. The point was to demonstrate, however, that the controllers worked effectively, and we did that. And another interesting thing we learned is that as you increase steam flow, everything else held constant at higher viscosity. You need about another normalized pressure, which is effectively where we begun. You need another one of those unit pressure differentials to break through this new interface created by higher steam flow. So the image on the left-hand side illustrates what we learned from our steam flow side of things. That's a still image of what's happening during C1-2, which is where the sludge flow plummeted and the steam flow had to be reduced because of a falling solder mean diameter. And that was counterintuitive. We didn't realize we'd need so little steam flow. But it's because the atomization characteristics changed. So instead of that nice flowing system of bursting events, we see these globs of biosludge because it's very, very low biosludge flow slowly bursting away from the nozzle and small droplets being ripped off. Our objective was to demonstrate that smart atomization can work for a 100-fold increase in viscosity. And of course, our motivation is environmental stewardship to address multiple problems with one solution. Number of learning points. This coupled controller system does maintain atomization quality and biosludge pumping requirements for 100-fold increase in viscosity, and we're not showing our mesh independence work. In the future, we'd like to add information to well-known correlations such as this from Lefebvre, showing solder mean diameter as a function of reciprocal Weber number, density ratio, Ohn-Surge number, and gas-liquid ratio. Our models experienced these changes in Ohn-Surge Weber and gas-liquid ratio with a 100-fold shift in viscosity. What we don't know is what the final gas-liquid ratio should be. That's why I marked it in red, because our steam bottomed out due to numerical limits. We couldn't let it finish. But preliminary assessment is this equation actually holds reasonably well throughout the experiment we tried. And thank you. We'll entertain questions at some point.